All right, thank you for coming back. First of all, announcing a mistake that I just made 20 minutes ago. The smoothing operator in the Cone-Nuremberg class is mapping from damper distribution to C-infinity functions. This mapping from S prime to S will happen later for a different calculus, which I'll mention for the scattering calculus. All right, so well, let me continue. As I said earlier, that I'm going to continue with composition of pseudo-differential operators. So as I said, that one feature about this quantization is that you can relate the operation and analysis side to the algebraic side of symbols. So in particular, we have the following. The theorem is that pseudo-differential operators can be composed, or in fancy term, that pseudo-differential operators form an algebra. So what do I mean is the following, that assume I have two CDOs. A is an mth order CDO, and B is an lth order CDO. Then I can compose them to get a different order CDO. That's A composed with B is going to be in m plus l's order. And moreover, in the symbol level, I have that in the principal symbol, it has a product. So the first property is that the principal symbol of this composed operator, which I know that it's going to be m plus l's order, it's just given by the product of the two symbols. And using this, immediately we see that if you compute the commutator of these two operators, so this AB, this is just defined to be AB minus BA. And if you compare AB and BA in the leading order in the principal symbol level, you will see that they're both given by the same algebra, by the same algebraic quantity, so it goes to 0. And therefore, by my principal symbol definition, I know that it's going to be in a lower order. So this commutator is going to be in m plus l minus 1 level. OK, so the first thing is that. And then this leads to the second important property, is that we can compute the principal symbol of the commutator. That it's going to be m plus l minus 1 order. This. And this is given by the important formula. It's given by the Poisson bracket of the two leading symbols. So let me recall what is Poisson brackets. So here, Poisson bracket. So that is for A, B, say two C-infinity functions. R2n. Then the Poisson bracket acting on this AB is given by definition. This is given by sum j from 1 to n d psi j a times dxjb. So this is not inner product anymore. It's really just regular product minus dxja times d psi jb. Okay. And I was reminded that I put a lot of extra bracket, or leaving a lot of extra brackets, so I'll just leave one here. Okay. So this is the definition of Poisson bracket, and well, those are two C-infinity functions. So I apply a Poisson bracket, and this will give me the principal symbol of this commutator. Okay. Now it might, if you haven't seen this before, it might look a bit mysterious, but let me do one example quickly. So, well, first of all, this is a 1D example. And it's not quite legitimate in the sense that the operator I'm going to use is actually unbounded. But it's good practice, or it's good example to, at least for simple computation. So that is, I'm going to take my operator A to be dx. So it's just a 1D example, so x just x. And operator B is multiplication by x. Okay, so multiplication by x is not quite a pseudo-differential operator here because it's unbounded. But let me say that let's make sense of that. And then you can compute the commutator of this. AB is just given by dx composed with x multiplication minus x dx. And then using chain rule, you immediately see that this is equal to I. Remember, my dx is 1 over I partial x. So I have an I here. OK. And on the other hand, you can apply the formula AB for the Poisson bracket. So here, remember, well, this dx, this principal symbol is just psi, and B, this multiplication, so it's just x. So it's a Poisson bracket of psi and x. And then, well, this is easy, just d psi times dxx. So that's 1. That's
the operator calculation being minus I.
Right. That's right. Sorry. Yeah, this is equal to 1. Yeah. Okay. And then, therefore, you can see, well, this is minus I times 1. Thank you. OK, so this is one simple example to see how this operator commutator translates to the Poisson brackets on the other side of the symbol side. So that's also one important relation between the quantization. All right. Now, my goal for the next 10 minutes is that at least give you some idea that how we can prove this composition. And we're going to use the machinery we set up earlier about converting symbols into y-independent ones, and how do we get back. OK, so proof. So first of all, I'm going to write A as op 0 of A for some A in Sm, Rn. In the sense that, well, by our previous theorem, I know that for any pseudo-differential operator, I can write it as using a symbol that's independent of y. OK, so the first time I'm using this. And then, well, suppose U is in the Schwartz class, then let me compute this composition on U. OK, so, well, how do I write it? I write it as 2 pi to the minus n. So I'm going to use the quantization of A and leave B there for now. And this is going to be written as e to the I x dot psi, A x psi, because it doesn't depend on y. And BU is going to be considered as one function that's being acted on by A at this point. OK, so far I'm just using the definition of op A here. OK, now here, what I'm going to do next is something called oscillatory integral test. But let me first write out the thing I need. So let me write E psi x is defined to be this e to the I x dot psi. OK, so here I'm just introducing a symbol, a notation here that this is a function of x, but has a psi as a parameter. All right, and well, we have the following, that Bu psi, this is given by Bu acting on x psi, well, L2 product with x psi, and this is equal to U B star x psi L2. OK, so this is really not much. This is just writing out everything by using Fourier transform in acting on temporal distribution. And the second line is just using the L2 duality, and I haven't even defined B star. B star is defined by using this relation. And however, we know that, so first of all, this can be written like that. And the B star, as we saw earlier, that this is adjoint of a pseudo-differential operator, and therefore it's still a pseudo-differential operator of the same order. And therefore, what I'm going to write is I'm going to write B star as op 0 of a symbol, which is independent of y. So I'm going to use this notation b prime bar because it has adjoint stuff in it. So I know that b prime is in the else order. Okay. So far, everything really just follows definition of Fourier transform. And here, it's again, we're using this theorem that for any pseudo-differential operator, you can write it as a y-independent symbol. And this time, I'm applying to B star. All right. Now, before I move on, let me, okay. Actually, I can use this board here. Right. Let me talk about this B star E cosine. So this is something that's going to be useful for its own good. Oscillatory integral test. So that is, I want to write this B star E psi in a way that it's actually not hard to see what this is. So I'm going to write it as the following. So this is actually just equal to op 0 b prime bar E psi acting on x. So that's not doing anything. I'm just saying that b star is equal to op 0 b prime. And the next step is that, in fact, it's very simple to compute it. It's b prime x psi times E psi x. Okay. So that's a step where I'm going to show in a moment. Okay. And you can see that once we have this and put in there, it's, everything will become obvious that what's happening. All right. So this is a step that I'm going to explain a little bit now. I think if you haven't seen this before, it's good to see it for once. So well, what's happening here is we're going to use this fact that for this function e psi that I defined above, if I take the Fourier transform of that in the temporal distribution sense, and here, because psi is already used as a parameter, I'm not going to use it. So the Fourier transform side, I'm going to use eta as my variable. And this is going to be, well, this is really just equal to 2 pi to the n delta function of psi minus eta. Okay, so you can make sense of that using temporal distribution. Okay, so that's just the, or formally you can just write it out and see that's a delta. That's a delta function. All right, and now using this, let's compute this op b star, op b applying to E psi. So op 0 b prime bar applying to E psi, acting on x. So this is going to be equal to 2 pi to the minus n, acting on e to the I x dot eta, b prime x eta bar, because that's an E psi eta d eta. Okay, so again, this step is doing nothing. I'm just writing out the quantization. And the next step is, well, that's easy. I'll just put in the definition of the E hat. And this is 2 pi. There's no 2 pi to the minus n anymore because there's a 2 pi to the n here. So this is e to the I x dot eta, b prime x eta bar, and replacing this by delta psi minus eta d eta. All right, we all know that delta function will pick out this number, so that's becoming e to the I x dot psi, because, well, you can see that, and b prime x psi bar. All right. So this is called oscillatory integral test in the sense that you acting on those oscillatory integrals, what you get is just the product type. Okay, so this picks out the symbol. Okay, any questions so far? Okay, so this is just the, if you believe in all the action are proper, then it's just algebra. You can test that. And then I'm going to use this information up there. So what we have here is the following. So bu hat psi, this is equal to uy, and with b prime y psi. bar e to the I y duck psi L2. Okay, so what I'm using is just this BU hat has this form where it places B star e psi into this form here. Yeah. All right, so well, at this point, I'll just write out everything, and you'll see that it just follows by algebra. So e to the minus I y duck psi B prime y psi u y dy. And again, well, because this B bar, because I have a complex inner product here, this bar disappears. All right. Okay. Now finally, I'm going to put it back to the first line there, and what we see is the following. So AB applied to U is given by the following form: 2 pi to the minus n of e to the I x minus y duck psi a x psi and b prime y psi and u y dy d psi. All right. Any questions so far? All right. So you can see that I'll just pick out this, and that's the symbol. And again, there's some technicality here that there's a decay issue here. So I'm going to, well, the one convenient way to say this is I'm going to start with when everything is convergent, meaning that I'm going to assume enough decay, then I can approximate with nice enough symbols, then you can get there. Okay, but let's say that at least algebraically everything makes sense. And that's my symbol. And in particular, it's very easy to see that AB is indeed in this symbol class, is indeed a pseudo-differential operator of order m plus L, where the symbol AX psi, B prime Y psi, that's the symbol, and this is in Sm plus L, R2n, Rn. Okay. So here, in some sense, what I'm doing is that I converted everything into y independent by left and right, and then once they compose, well, you get back x and y. All right, so that basically proves the first part of the theorem, and the next product rule and commutator rules follow by the expansion. So let me explain a little bit of what's happening here. So first of all, we can check principal symbol. So, well, the principal symbol, just notice two things, that the principal symbol of A is given by this A, and which I'm defining by picking this op0 A. And the principal of B is given by this, sigma L, B is given by this B prime. And therefore, the principal symbol of B is given by A times B. Again, everything is modulo lower order terms. So since principal symbol is an equivalence class, there's no problem. So I should say that. Everything is modulo lower order terms. OK, so not much is happening here. But let me also mention the commutator. So again, if you haven't seen this computation, it's nice to see it at least once. So the commutator expansion is really just using expansion that we used before by saying that well, there is a relation between the symbols of the leading order symbols and second order symbol. Sorry, the sub-principal part. So this is, if I write my A to be op0 A, or the other way is to write it as op0 A prime bar star. So that's, again, not doing much. That's just saying that I can write it as an adjoint. And the symbol of the adjoint is given by this. And similarly, B is given by op0 B, and this is given by op0 B prime star. Okay. And then what we really have here is the following, that, well, first of all, the principal symbol of A is given by A. It's also given by A prime, and of course, everything is modulo lower order term. And similarly, B is given by B equal to B prime, and again, it's modulo SM minus 1 terms. Okay, so this you can easily check. And moreover, A, as we saw that the leading order expansion, or the expansion is completely determined, so modulo low order term. So A prime is equal to A plus I dx applied to d psi dot d psi A modulo Sm minus 2 terms, and B prime is equal to B plus I dx dot d psi B modulo Sl minus 2 terms. Because in the here what I mean is that the diagonal terms, so that's the leading order term. Okay, and in particular, what happens here is that the commutator of A and B, if I write it as C, where C can be written as equal to A x psi B prime y psi minus A prime y psi times B x psi. By definition, that's my symbol. And then you'll see that you can put everything in there, put this A prime and B prime there. You'll have an algebraic expression which has 4 terms. I'm not going to write it out because I don't have time, but eventually you'll see that this is given by, you can write it again, apply this algorithm. Convert this symbol, which has x, y, psi, 3 things, into a symbol that doesn't depend on y, because that's what I want. And then using this, you'll see that, okay, so that's really bad. I'll start with another board here. Keep this for now. Using this, you'll see that the C tilde is determined up to the second order term here. And so C tilde is equal to C x psi minus I dy dot d psi dx psi C dy x psi. So this is, again, modulo lower order terms. And then you'll see that this C tilde is just given by minus I AB. Again, modulo Sm plus L minus 2. Okay. So let me mention 2 things. Okay, this part is a bit rushed, but I really don't have time. So first of all, this is not the only way that you can you can prove the commutator rule. That in some sense, it's not a conventional way. The conventional way will go through stationary phase expansion, but I'm not going to do that for this lecture. So this is a quick way in some sense, but it does rely on this this asymptotic expansion of this operator that we just obtained. And then using that, you'll see that everything just goes through the algebra, and then you'll get there. And everything just comes from the second term here in the expansion. Okay, so this finishes the commutator argument, and this will be useful, I believe, in Andres's lecture. Okay, now let me mention a few more things before I go to a different symbol class. So, well, we talked a lot about the definition and algebraic properties, and one thing that's useful for pseudo-differential operators is that it has nice mapping properties. Mapping properties. So one important thing is that well, it does map has bounds for when it acts on subglyph spaces. So, well, let me define the subglyph spaces as the completion of space under this HS norm. So that's, again, just a recall. This is psi s, u hat psi, now 2. Okay, so the usual that you just, and I can define it for any s. And then the important theorem is the following, that for any, fix any Sm, then, say, so assume A is a an mth order pseudo-differential operator, then A is a bounded operator acting from HSRn to HS minus M Rn. Okay. So that's the theorem. And again, one thing you should think about, well, one thing you can think about is that this m's order, this m here is really kind of the order of the differential operator. So, well, here it appears as a Sobolev regularity. Okay? So if it's a regular differential operator, you can immediately see that. And I'm not going to do the proof of that, but I should mention that the difficult part is really to show that if M is a zeroth order pseudo-differential operator, then it has an L2 boundedness, meaning that it acts from L2 to L2. After that, everything is just by commuting this Casayas. So that's simple. But the L2 to L2 boundedness is really a non-trivial proof. Okay. So if you're curious, you can see, well, there are a lot of places for this proof. So I'll just mention it here, and it may appear in the end. And I only have half an hour. Let me now. I want to consider this elliptic operator, this Laplacian plus 1 in the beginning. But before that, I want to introduce a different symbol class because I need some compactness. So, well, so the sixth part is scattering calculus. And I'll be really brief in the sense that a lot of things goes in parallel. So I'll just basically mention all the things that I mentioned before, but for a different symbol class. Okay, so I'm going to introduce this symbol class, SML Rn. Okay, so this is those functions, so C infinity functions, such that if you apply this same kind of operation, applying dx and dx psi on this function ax psi. So this is less than or equal to C alpha beta. I still have a psi decay here, then m minus order beta, but I also have an x decay here. So this x is L minus alpha. Okay, so that's the difference from the Kohl-Nirenberg symbol class. And here, well, you can say that this m, the first number m, is usual. So this is, you can say that's the differential order. And this L, this is the growth of x in coefficients, you can say, in coefficients of the differentiation. Okay, now let me, right, I can use that board. So let me say a few things that some of them are similar to this, to the Kohl-Nirenberg class, but there's one last thing that's very important that's different. Okay. So, well, the first thing is that this SM0, you can view it as a special class of the Kohl-Nirenberg symbol that I defined earlier, but there are more things. Okay. And the second is that I can define those scattering CDOs. So by similar notation, this psi ml just means that the symbol is in this SML class. All right, now let me talk about a few properties. So property number one, that again, you have a principal symbol map. But this time, the principal symbol map is not only taking the leading order of m, but I'm also considering this the decaying x. So that is this principal symbol map. I'll do it as sigma ml. This is mapping from the class of pseudo-differential operators of ml order into the following form, into the SML quotient of Sm minus 1 and L minus 1. Okay. So again, for this, there is a similar type of expansion, asymptotic expansion you can do for this, but you'll see that because of this, the next term is I dx d psi, and because of the order here, this x is also decayed by one order. So that's why the next order down is already m minus 1 and l minus 1. And then the second thing is, well, we again have product rule. I'm not going to write out the whole thing, but basically this is saying that if you compose two pseudo-differential operators with two different order, well, this is going into m plus, you just add two numbers. Okay. And the commutator is similar, well, exactly the same calculation. That is sigma AB is going to the principal symbol of the commutator is given by minus I of the Poisson bracket of the two principal symbols. So nothing's different. And the third thing is, the fourth thing is that the adjoint is again given by the same formula. So for adjoint, if A is in this class, then A star is also in the same class. And again, we have the correct symbol correspondence that the principal symbol of A star is given by the principal symbol of A, but taking the complex conjugate. Okay, and now here comes the thing that's different, and that's going to be useful later, which is the mapping property. Okay, so the mapping property is the following: that if A is in ML order, then the following operator is bounded. Then we have a bounded operator. Well, let me just write it this. A acting from x to the t hs Rn to x to the t plus L hs minus m Rn. This is bounded. Okay, so that's the difference. Here, what I meant, what I mean here is that those are weighted Sobolev spaces, in the sense that you can just view it as functions. The functions are in the form that it's given by xt, where this is a Japanese bracket again, xt times an element in hs. So that's called weighted Sobolev space. And what's happening here is that because my A has this extra decay here, and I get it here. Okay, so this is represented by this extra weight here. And again, the difficult part is to show that if A is in psi 0, 0, then you have an L2 boundedness. And then after that, it's really just commuting this weight in there. Okay, now using this, I can talk about the residual or the smoothing operators. So I can define the following. This is number 6. So this is a residual class, which is a psi minus infinity. Rn. So this is defined to be the intersection of all M and L. So this is all the pseudo-differential operators in this calculus, in this class. And well, now for this one, finally I can say that this is a class that maps from S prime to S. Okay, and because this is because we have this extra negative infinity here, which tells me that the symbol class decays both in x and psi. Okay, so this helps me to get this. Okay. Right, All right, and well, in comparison with the Kohn-Nirenberg symbol class, what we see here is that if you take an operator here, then the integral kernel of this operator is actually in Schwartz functions, not just in C-infinity. Okay, so that helps. And another thing I should mention here, which is very different from the Kohn-Nirenberg symbol class, is that we have the following functional property that if you take a weighted sublift space with a good weight, then we have a compactness here. So this sitting L2 compactly. For any s greater than 0 and t less than 0. Okay, so in the sense that as long as you'll need a bit of decay here, and then this will help us for the compactness. And in particular, using this, what we see here is that those pseudo-differential operators in this class is going to be compact operator on acting on L2 if I assume that m is less than 0 and L is less than 0. All right. Because by using this, by using the mapping property here, you can see that if I act on L2, and because of this ML here, I'll map into a weighted space, where the weighted space is sitting into L2 compactly. Okay, so that's very different from the Kohn-Nirenberg class. Okay, and that's going to be useful. All right. Okay, finally, I can talk about the second to last part of my lecture, which is elliptic parametrics construction. Any questions so far? All right, well, let me continue then. So this is elliptic parametrics construction. Okay, this is dying. Here's a different one. This is scattering calculus. Okay, so, well, let me first mention one thing that I kind of mentioned before about this asymptotic expansion. So that is, we have the following theorem, that for any infinite sequence of pseudo-differential operators in the following form, such that for Aj, so J is from 0, 1, da, 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 da. So if Aj is in this class, psi minus J, then there exists a pseudo-differential operator in the class psi 0, 0, such that A has this correct asymptotic expansion given by those Aj. In the sense that, again, this is not equal, in the sense that that if I take out the first k-sum, I'll end up in a better symbol class, j from 0 to n minus 1, Aj, this is in psi minus n Rn. Okay. So again, this is, in some sense, it's if you haven't seen this before, it might look weird. So what this is saying is that for any Aj, no matter what kind of convergence you have, you'll always be able to construct a pseudo-differential operators in this property, with this property. But this is not saying that you can just sum up Aj and it's convergent. It's different. And in order to show this, we need the technique of Brawl sum that I'm not going to touch upon for this. But let's assume that this is good. So what this is saying is that if you give me each term, I'll just be able to construct a pseudo-differential operator out of it. And that's going to be useful in my construction. Now let me state my theorem. So the theorem is that for any elliptic pseudo-differential operators in the in the scattering calculus, I will be able to construct almost an inverse in the sense that it's up to this residual class. Okay. So the theorem is the following, that assume I have an operator P in psi ML Rn. And I'm assuming that this is globally elliptic, which I'll define in a moment. So, i.e., the principal symbol of this operator satisfies the usual elliptic, in this symbol class, satisfies the following, that there exists a positive constant such that this operator, or this elliptic symbol, evaluated outside a compact set is going to be uniformly bounded by this x to the m and psi to the l. Okay, so as expected, when x plus psi is greater than equal to c. Okay, so one way to remember is that it's very similar to the usual elliptic definition in the sense that you take the symbol and then it's uniformly bounded. But of course here, I'm taking the symbol class, so it's reflected there. All right, and I should also mention here that this globally elliptic definition is independent of the choice of the principal symbol. Again, principal symbol is defined up to this equivalence class, so you have a lower order term. But lower order term doesn't matter here because this is a leading order term. You're comparing for that. All right, so let me state my theorem. Then, if this is globally elliptic, then there exists a parametric, which is in psi minus m minus l Rn, such that PQ is almost identity plus remainder term, which is in this residual class, psi minus infinity, and same for QP. Okay, so that's the theorem. All right, so essentially this is saying that if it's an elliptic operator, then I can invert it. But I cannot quite invert it, but there's a residual term there. Okay, so before I talk about the proof, let me say two remarks. The first remark is that using the theorem, what we have here is that this operator P acting from these two weighted subgroup spaces, Hs to Rn, to x to the t plus L Hs minus m Rn, this is Fredholm. For any S and T. So it's not only bounded. If I'm assuming that it's globally elliptic in this sense, then this is Fredholm. Okay. So this is a standard way to show that. Well, how do you show something is Fredholm? You find a parametric so that you can invert it up to a compact operator. And here I do have a compact operator here because my psi minus infinity, as I said before, that because of this extra decay in x, I do have a compact operator here. And therefore, it's Fredholm. Okay. So that's the first property that can immediately follow, and that's very useful. Okay, so that's the first remark. And the second remark is, talk about this example that we started from section 0, that, you can check that this Laplacian plus 1 is psi 2, 0 Rn. So that's one example of this globally elliptic operator. And the second example you can do is Laplacian plus x squared minus, okay, let me write e. This is in psi 2, 2 Rn, where this e is just a constant. It's a real constant. Okay, so those are some of the examples you can apply this theorem. And however, sorry, I shouldn't say this. Right, for those two, we can apply the theorem. However, I should point out one thing. If you consider the usual Laplacian, this Laplacian is this is again in this correct symbol class, psi 2, 0. But this is not elliptic in the scattering calculus. Because my requirement of this x. It is elliptic in the Kohn-Nirenberg calculus, if you remove the requirement of this x. All right? So for one thing, well, of course, that's, I mean, everything here is just a classical. What I'm saying here is that Laplacian plus 1 is a Fredholm operator. But Laplacian itself is not. Okay, so that's all it's saying here. Okay, so this is just trying to connect to something if you know about the fact before. So what this is saying here is that that's, in some sense, it's a major difference between scattering calculus and Kohn-Nirenberg calculus, in the sense that one, you can get this Fredholm property because you have the residual class as a compact operator. But in the Kohn-Nirenberg class, you don't have that, so you cannot do that. All right, so I still have about 10 minutes. Let me say a little bit about the proof so that you don't feel like I stated this asymptotic expansion for nothing. So the idea is a very standard technique, basically called inverting the symbol, and then you try to do it from the symbol level. So proof of the theorem, just invert the symbol. Okay. So first of all, well, what we do is we first pick a representative of the principal symbol. Let's call it P0. So this is sigma P. Again, this is a sigma MLP, it's really. Okay. Again, it's defined up to the lower order term. And I'm going to define the following. Q0 is defined to be up 0 of a different symbol, Q0, where this Q0 is equal to 1 over P0 outside. Well, okay. Let me not say outside. For x plus psi greater or equal to 1. Okay. So, well, the basic idea is that I secretly know that the inverse is something like 1 over P0. But I cannot quite do 1 over P0 unless I'm in a safe region where I know that you can invert that. So the safe region is that if x and psi are big, then because of ellipticity, I know that I can do that. All right. And in the interior, I'll just patch in something smooth. So by ellipticity, we know that such EQ0 exists. And moreover, the important thing is that you can check that this Q0 is in the correct symbol class, that we know that Q0 exists in, and it's in S minus M or minus L. Okay. So, well, again, this is not such a trivial statement that you can kind of see what's happening here is that because of the ellipticity assumption there, if you invert it, then those numbers all got inverted. But you also need to check that the differentiation follows the correct symbol calculus. So their elliptic calculus, well, their ellipticity will also be used. But let's say that we know that. And for example, if it's really polynomials, then you do have that. Okay. Then once we have that, well, one thing we know immediately is that PQ0 and Q0P, they are in psi 0, 0 by the principal simple calculus. And then the second thing we know is that the leading part, Q0P equals to sigma 0, 0 PQ0, this is just equal to 1. Okay. And therefore, what we see here is that this remainder, which I defined it as identity minus PQ0, so let's call it R1. This is in psi minus 1 minus 1 Rn. So, well, if PQ0, the principal symbol is given by 1, then that means that the 0's order is equal to 0. So by my principal symbol definition, that means that it must be in the next order. Okay. And similarly, I can define this R2 equals to I minus Q0p, and that's similar. Okay. Now, the next part is just inverting the remainder. So the next part, we're going to do this Neumann series. It's not really a series, but it's a Neumann asymptotic expansion. By inverting this 1 minus r. So that is, I'm going to construct Q1. This is in psi 0, 0 Rn, such that Q1 asymptotic expansion is given by j from 0 to infinity of r to the j, where r1 to the j. So r1 is here, and I know that, well, if you keep r1 is in psi minus 1 minus 1. I think I did something wrong here. This is minus 1 minus 1. Oh, sorry, 0, 0, because there's a leading order term 1 there. So R1 is in minus 1, minus 1. R2 is in minus 2, minus 2. So by my previous theorem, I can always get the Q1, which has the same asymptotic expansion. And in particular, well, secretly, I know what I'm doing is really just doing this. All right. And then define my Q to be Q0, Q1. And this will do the trick that PQ is going to be I plus, I plus an order term, leading lower order terms. Okay. So what's happening here is that while I will apply this 1 minus r, I'll multiply by a 1 over 1 minus r, so everything goes through. Okay. And similarly, you can invert this 1 minus r2, and you get a q2. So that is q prime equals to q prime will satisfy q prime p equals to identity plus psi minus. Okay. So to construct two things, and then the last step is just to show that the two things I constructed from the left and right inverse, they are really different only by a residual order by this simple trick. So that's just apply P. So we get, if you apply Q to this, to the right side, apply Q prime to the, apply Q to this side. So consider this. Okay. Then you'll see that the Q minus Q prime is in the residual class. So therefore, this parametrics is really defined, uniquely defined up to this harmless term. All right. So that does it. Okay. So this is a very common construction for elliptic operators in the sense that all we're doing is just invert the symbols. And why can we invert the symbols? Because the symbol has the correct bound there. Okay, so that's in one word, that's what I did for the last 5 minutes. Okay, now finally I only have 5 minutes, but I'm asked to cover a little bit about studio differential operators on manifolds. So I'm just going to write a few remarks. A bit about ideals on manifolds. Okay. So first of all, let me talk about compact manifolds. So for compact manifolds, you can define all those pseudo-differential operators. So suppose. And the key of that is that all those calculations that we did before, most of it is invariant, coordinate invariant. So all you're doing is just to, for a compact manifold, take coordinate patches, and for each patch, define this pseudo-differential operator, which has a correct bound and stuff, and then you patch them together, you'll get this. Okay. So that's the key is coordinate invariance, which we didn't talk about at all. But if you're interested, you can check the lecture notes or check any book about pseudo-differential operators. There will be a calculation to show you that this is the case. Okay, so everything goes through. And, but there's one thing I want to mention that's different, which is the symbol. So first of all, the full symbol of a pseudo-differential operator on a compact manifold is not globally defined, because what you're doing is you're patching together things already. But the principal symbol, okay, well, let me just write principal symbol here. Principal symbol is a function on T star m, on the cotangent bundle. Okay, so it might seem like it's out of nowhere at this point, and I don't have time to explain this, but let me just give you a quick example. So example, if you take a vector field x and take the operator to be minus ix, so this is in the Kohn-Nirenberg class, that's a first order operator. Okay, so the x is just in some sense it's d by dt. All right, and then the principal symbol of this operator is given by psi paired with the vector field at that point. So here, x, you can say that it's a variable m, and this psi is a variable on this tx star m. All right, so that's how it works. And locally, you can check that this is invariant. And another thing I want to quickly mention here is that the commutator rule also goes through that. But here, the Poisson bracket, again, you'll need to either you can use local charts, so that everything just goes as before. Or there's a fancy term to say this, that is T star m is a symplectic manifold. So the Poisson bracket just carries through. There's natural Poisson bracket. OK, so that's everything about what I want to say about compact manifold. And for non-compact manifold, well, things are more complicated. In particular, you do have infinity to worry about. So okay, I only have 1 minute, and maybe I'll just say it, that for a non-compact manifold, you'll know, in some sense, you should know what's happening as x goes to infinity, because when it's non-compact, it goes somewhere. And then you'll need to specify boundary conditions. For example, M is a scattering manifold. In some sense, that means that it has a Euclidean end, or you have a different manifold, you have different ends. And then then you can define the pseudo-differential operators there, but you do need to know what's happening near the end. OK, so that's all I want to talk about. Thank you. Right. What I meant is that outside the compact side, it's equal to 1. Yeah, but that's good enough. Yeah. I mean, what I really care about is this R1 is in this symbol class, because that only cares about to go to what's happening into infinity. So they match outside, so that's fine. Yeah, I should say that there. Yeah. Thank you. Right. OK, what I meant is that this is an elliptic operator. This is just a psi 2-2 example. Right. Yeah. OK, let me just. OK, I'm not going to write it. This is elliptic. This is not. OK. Yeah. Uh-huh. Yeah, yeah. Right, correct. Right. Right. Yeah. Great. Thank you for explanation.